Welcome to this video on applying the Biot Savart law. In this video, our main goal is going to be to put the Biot Savart law, specifically the equation, into practice here where we have a current carrying loop and we're trying to figure out the magnetic field. So remember, the Biot Savart law, the whole point of it is to find a value for B, which is the magnetic field at some location. This was very similar to finding the value for the electric field around a charge distribution using the differential form of Coulomb's law. Now, analogous to that, we're using the Biot Savart law. And of course, we talked about in a previous video when we were talking about Ampere's law that we could do the exact same thing using Ampere's law if we had a specific circumstance. We could also use the analogy that for the electric field, instead of using Coulomb's law, we could use Gauss's law to figure out the electric field at a given point. So when you are getting kind of stuck in all the substitutions in the math today, take a step back and just remember we're trying to figure out the magnetic field, and we're doing it by employing the Biot Savart law, which we'll get into in a second, and use that in comparison to Coulomb's and Gauss's laws. Now you may want to go back and watch some of those old videos if that helps to put things into perspective. Additionally, I have a list of some steps here that can help us just guide us setting up the integral that we need to use, and so you can screenshot the screen if you'd like to keep this. So the very first thing that we're going to do here is determine the direction of the magnetic field at the point in question. So the point in question here is point P. It's r over 2 units away from the central point of this loop of current carrying wire. And I'm going to go ahead and draw in the direction of the current here, which is going to be this way. So over here I have a view of this where if you rotated this end down and this left end up, you get this picture. Here we have a view from the top, so just kind of rotating this back a little bit so our current would be like this, counterclockwise. And we're going to use these three views just to help make things a little bit clearer. So we're going to use right-hand rule number 2, is what I refer to it as. Right-hand rule number 2, where our fingers curl in the direction of the magnetic field and our thumb points in the direction of the current. So if I put my thumb here in the direction of the current, then I can see that my fingers would curl upwards in the space in the inside of the loop. Now if I look at this view over here, I would point my thumb downwards and my fingers would of course be pointing kind of curling out this way and going back and around this side. And then finally if I look at this view, my fingers would be coming out of the screen in this region of the loop. Now we have to consider that there's not just this one straight wire here, that it changes direction, and so every little current element is contributing to the magnetic field there. And if you put your thumb in each direction of the current at a specific point, what you'd find is that the magnetic field components all kind of curl or curve instantaneously at point P, kind of up to the right, up to the left, up out of the screen, up into the screen. So you can imagine that kind of distribution here. So if you were looking at it from this perspective, we'd have these contributions would be all the way around here. From this perspective, we'd look at it like this. Now what we're saying essentially is that this little current element here that I'm going to label as IDL, that little piece of current is contributing to a piece of magnetic field which is dB. Okay, and then obviously this one would be making this dB and so on and so forth all the way around. So these are little tiny elements of the magnetic field that are being constructed by each tiny little element of the current. And as we have done several times before, we know that we can use integration to help set up this procedure. The next thing we want to look for, though, is symmetry. Because if the point that we're trying to focus on is symmetrically located in relation to the shape of the wire, then we'll be able to cancel out some components. So let's take a look at what we mean by that. First, I'm going to just get rid of some of these vectors here just to make things a little bit cleaner. so that we can see a little bit better. Well, we have this situation here where we have a component horizontally along here and a component vertically along here. So we're going to call the vertical component dby, and we're going to call the horizontal component dbx. Now keep in mind that we could call this db horizontal and db vertical, which might be a little bit better actually in the grand scheme of things. But either way, we're okay. Now if I rotate this, now I can see that I'm calling this component, or if you draw it over here, it's the same thing, dby, and then I would have this component be dbx. So this is just looking at it from a different perspective, so you can rotate this in your head. Well, if we look at it here, all of the horizontal components, or the dbx components, we can see that those all will actually end up canceling one another out because they're always pointing in opposite directions with an equal magnitude. And so what I end up leaving here is only the vertical components. Now, I'm going to refer to that as only the x components being deleted and only the y components remaining. So if I erase out all of those components, and I see I just have the dby components left in this case. Now what I'm going to say is that if I were to add up all the dby components, then I would get the total magnetic field at the position in question. And if you think about all these vertical components adding up, we'll get a net direction of the total magnetic field pointing straight up in this case, or straight over in this case, or straight out of the screen in this case. So you can see that there are a lot of different components here that we need to take into account as we set this up. The next thing is we're going to write a differential form of the Biot Savart law due to a tiny current element. So we're going to focus primarily right now on just looking at one of these little kind of dby elements, and then we can do a integration to add up all of them to get the total value. So what we're going to do here is write out the Biot Savart law, and the Biot Savart law in one form at least is going to be dB is equal to the constant mu naught over 4 pi. Now we're going to multiply this by the current I dl, so this is a small current element, cross, and I'm going to put the unit vector r here with r squared on the bottom. Now keep in mind that this could be cross r without the unit vector over r cubed, and it would be the same thing. Now I have to keep in mind here, this is dB would be one of these total current elements, and I need to only find this y component of the dB. So I have to figure out what that's going to represent. So let me go ahead and outline the direction of r here, which would be this distance, but this direction. Okay, so I'm going to go ahead and draw that into each of these drawings. So we'll go ahead and we'll put here, this is that distance r, and the direction of the r vector is kind of pointing up towards this point, which makes sense. Now if I draw this on my other diagrams here, I would see it kind of like this. That's that same r value here and here, and then on this image it would kind of look like a straight line along the radius of the loop, although not equal to uppercase r, but rather lowercase r, the way that I would see it in this perspective. Now, we have to consider a few different things. Right now, we're trying to figure out the y component of the total, or of an element of the magnetic field, in order to get the total. So I'm going to use this angle over here, and I'm going to call this angle phi. Okay, so that angle is labeled as phi, and I'm going to say that that angle is going to be equivalent to this component over here, phi. Now phi tells me that the y component of any dB vector is going to be the cosine of phi. Okay, so we would have here dby would be the same thing then as writing dB times the cosine of phi. Okay, and when I've summed up all of these little components, I should be able to get my total value. Okay, so ultimately what I'm going to write here is cosine of phi onto this equation. Now, the next thing that has to happen, and this is a part that's a little bit more complex than using Coulomb's law in most cases, we see here that we actually have a cross product. And this is the cross between the dl vector, so that's a little tiny piece of the current length of wire, and the r direction. Okay, so the r direction is this, and the little current element is right along here. So I'm going to look at this now from the top because I think it makes it a little bit easier to see. So here's the r hat vector. Now I'm only drawing it this little short piece because I want to think of this as just the direction of r. It's not the total length of r, but it points along the length of r. So imagine that being this piece over here so that you can kind of think about it in different directions. Now the current element IDL is going to be pointing tangent to this coil of wire like this. So we see we have a 90 degrees between the dl vector, if I draw it here, or it would be this direction over there, and so on and so forth. In this plane it would also be down. This one's harder to see that it is 90 degrees. So what I need to do here is just verify that what I'm writing now is going to actually be the correct thing that I'm intending to write. So dby is equal to mu naught over 4 pi times I dl over r squared, and this cross product between r hat and dl is going to make this sine theta. Now, you may be wondering what happened to the r. Well, remember, this is just the unit vector direction, so its value is just 1. And once I've shown that it's a cross product, I can get rid of that. Now I need to add this cosine phi onto the end here because that's the part that makes this work. Now we know this is 90 degrees between the two vectors, and it's a cross product, so we're going to be using the sine, and the sine of 90 degrees is 1. So essentially what we can do is actually just leave this out altogether. So that's great because it eliminates something else that we need to be a little bit stressed about maybe, and we have to write dby is equal to mu naught over 4 pi times I dl over r squared times the cosine of phi. At this point, we're actually ready to integrate in the sense of we know that eventually what we'll be doing is integrating here to get our total value. But the problem is that we have DL, we have this phi value. There's a few different things. Now the phi value stays constant all the way around. The R is staying constant all the way around. So we're working our way around this circle, and we're ultimately going to work our way from 0 all the way around to 2 pi. And we'll get to that here in a second. So let's see now if we can come up with expressions for the different components so that we can write them in terms of r for the circle, and maybe this value which I told you was r over 2. Okay, so let's go ahead and see what simplifications we can make here and what we can pull out of the integral to find out what we are actually integrating. Well, the first thing that I see is that the cosine of phi here can actually be written as big R over little r. So I'll go ahead and show that in here. I'm going to leave out the integral sign for a second just to save time since this is already a pretty long video here. Okay, so this is going to be big R over little r. So we've already got some things going here for us. The next thing I'm going to do is take a look at this r value here and write it maybe in terms of these two values because I know this constant r here actually is useful. So I'm going to say I'll step aside here and say that little r, that distance, right, is equal to the square root of r squared, this is big R squared, plus r over 2 squared, or r squared over 4. Okay, so that would be this length over here. And if I do some simplifying here, what I find is this would be 4r squared over 4 plus r squared over 4. And what I end up with then is root 5 over 2 times r. Okay, so this is the value that I can put in here. But I can see that there's a simplification already that can be made here. So I'm going to go ahead and do that. And I have mu naught over 4 pi times I dl times big R over r cubed. Okay. Next, what I'm going to be doing here is actually putting in this expression for r cubed into the equation. So let's go ahead and do that. So I have mu naught over 4 pi times I dl times r over root 5 over 2r all cubed. Now let's go ahead and put our integral back in here. But I'm going to put anything that is a variable, anything that is constant out front. So I'm going to have the mu naught. The I is constant, which I'm not sure if I mentioned, but yeah, we have a constant current here, over 4 pi. This r is constant, as is all of this. So root 5 over 2r cubed. And then we're integrating with respect to dl. Now, the limits of integration here are going to be from 0 to 2 pi. And let's talk about what this is referring to in terms of the picture. So if we scoot back around here, we see that what's essentially happening is we're working our way, let's say we start right here, we're working our way around this circle, adding up all those elements. So technically we're spanning over an angle here, let's call that angle alpha, as we work our way completely around. So when we do the integration here, what we essentially get is mu naught I times r over 4 pi, and then all of this again, root 5 over 2 times r cubed, and then 2 pi uppercase r. Okay, so that's essentially what was all added up around the loop. Now we want to get a final expression that is simplified because this is a little much. So let's take a quick look at that. So I'm going to switch over to here to work this out. So bear with me here. I'm going to do it step by step because I think for some people it's not as obvious. So let's go ahead and start. So we have mu naught I times r times 2 pi r. Okay, so we put all of this at the top, and now we have it all over 4 pi times root 5 over 2 times r, and that's all cubed. Okay, so the next thing here is we're going to do this cubing, and so I'm going to end up with mu naught times I times r squared, okay, times 2 pi over 4 pi times root 5 cubed, okay, over 2 cubed times r cubed. Okay, I'm not going to do some simplifications yet until I've made some other changes, just because there might be things I can group together. So I have mu naught times I times r squared over 2 pi, and that's all over 4 pi. And now this part over here is going to become 5 to the 3 halves, and then r cubed. And this is a complex fraction, so I'm going to move this up top here, and 2 cubed is 8. Okay, so let's get this a little bit more cleaned up now. So we have this mu naught, we have I. The r squared here and this r cubed will simplify. The pi will simplify out, and I've got 2 times 8 is 16, so mu naught I times 16 over 4 to the 5 to the 3 halves times r. Okay, 16 over 4, of course, is just going to give us 4, so we're going to have 4 times mu naught I, and that's going to be over, and now we have these two have simplified to the 4. 5 to the 3 halves is going to give us 5 root 5, and then that's going to be times r. So here we have the expression b is equal to 4 over 5 root 5 times mu naught I over r. So we have an expression here that gives us a nice approximation of what the total magnetic field would be at this point. Now I know that that can be a little bit cumbersome and a little bit overwhelming for some people, but go through it step by step and take a look at how we set it up. The simplification at the end is the least important part. The most important thing is, I think, identifying the directions and how the field is structured, and then you can add the math once you have that down. So I hope that helps. I'm sorry this is such a long video, but it is quite detailed, and I wanted to make sure that you got the best amount of details we could. So good luck, and we will look at some other situations later on.